Okay, let's begin our today's seminar. And our today's speaker is our playwright, Victor Aganesian, who will talk about one of the, from my point of view, one of the most promising trends in modern deep learning. That is linear differential equations, based on the paper which has received Best Paper Award on the last NIPS. And next week we'll have a follow-up made by Sasha, who will tell the further development of this model, so-called fjord model. So this is part one. Victor, please.
Thank you for the introduction. And hello everyone. Let me start from the plan of my talk. First of all, I want to show you how this approach appeared, and actually it was appeared from the analogy with ResNets, and then we will see that our model is actually ordinary differential equations, and we need to know how to solve it. And I will show you how we can do it. After that, we need to know how to train our model, because actually it's the analogy with neural networks, so we need to know how to train. And the main idea of this is a adjoint method, and I will show you it. And after that, I'll talk about experiments which was made by the authors of the original paper, and some preliminary experiments made by myself. So when we have ResNet, the output of actually the input of a new block is connected with input of previous block by skip connection and some function f, which takes inputs of the previous block. And I want to show that by f here and after that, until end of my talk, by f I will suppose not one layer, but maybe any amount of layers which are connected with skip connection. And I can rewrite my first line. You can see the second line is the rewriting of first line. And here n is a number of layers. And we can treat this as time, and we can try to go to the limit when n goes to the 0, and we will get ordinary differential equations. As you can see the first line, where theta becomes a function of time, and actually the new point we can add dependence of time in our function f. There was not same in the ResNet. And now
do we actually able to solve uniquely this differential equation if we do not put the initialization for the derivative at time 0?
Yes, we can solve this equation if we treat this line as our...
And it is enough to uniquely define the function.
And function f should be uniformly Lipschitz by z, and if some activations like relu and other, actually most of the activations are good for this purpose.
By good you mean they are just continuous? Or
Yes, and if we use these activations, we can get a unique solution.
Just one small question. Are the initial conditions is just 0, 0 or 0, 0 and 0?
No,
0,
initial
0.
conditions only at time 0.
At time 0, not at time t.
Yes.
Okay.
I just want you to treat this like analogy with neural network, when z at time 0 is the input of our layer and z at time t big is the output of our network. But for unique solution, one more time, only first line is needed. Here we can talk about theta. Actually, it can be given by another differential equations, or it can be just given as function. And authors of the original paper say it's just a constant. Constant that we use in our ResNet. So the same parameters that we use in ResNet now is treated as a constant function by of time t. And
it is incorrectly just you want to say that all theta n is just one theta. It doesn't depend on n. So
yes,
in the differential equation doesn't depend on t.
yes. In their paper, it's theta. It's constant. And if we treat this differential equation as continuous neural network with infinite number of layers, at each layer theta will be the same, and they will be connected to each other. I mean, if we change theta at one layer, all thetas will be changed. And how they add, depending of t, they at every layer they add constant channel with t as a channel of image. I don't know, did I say it clear?
It is something like Bayes.
Just if we see on our image as, for example, RGB channels, they add one more layers with constant channel just with T. It's just to add connection to make every layer not the same as previous, to change layers by time.
So, but this is in some sense just a technical detail.
Yes.
The most important is that we take t as an additional input,
Yes.
right?
Right.
So am I right that f should be the same? So residual blocks should be the same for the whole network?
No, and the explanation is exactly due to the fact that our f function depends on t explicitly. By changing t, and by changing t, we change the residual block. We change function f.
Okay, but the output shape of f should be the same.
Yes.
Thanks.
If we forget about t here, it will be just the same f every time.
And this would be the analog of recurrent neural network.
Yes. So, as you can see, it's ordinary differential equations, and I want to show you how we can solve it. I'll just give you an example where f is just minus square z, and the main idea just we need to get approximate value of time derivative, and the easiest way is just to treat this as z k plus 1 minus zk, and divided by the step of our algorithm. And actually other methods like Runge-Kutta and Adam they just approximate this derivative better than early method. And here I want to show you the difference between explicit methods and implicit methods. In the explicit method, we take right part of our equation in the previous time, zk, and we get just easy way to get zk plus 1, because it depends only on previous time. And in implicit method, we in the right part we put next time zk plus 1, and we get nonlinear equation to solve, and we need to solve it to get zk plus 1.
No, but this is a one-dimensional case. Or do we do the same in multi-dimensional case as well?
Yes, we do the same.
In ODE, it does not matter.
What?
In ODE, it does not matter. In PD, it will.
Okay.
And actually, some more details. In some, we have now some adaptive methods when h is change every time, and just to make our error, to keep our error as we want it. So h can be not the one for all our solution.
It can be function of time.
Yes, exactly.
And by changing h, we can control the accuracy with which we
in this method, we can change h to, we can make it smaller to get better solution. Mm-hmm. But in adaptive methods, we make error, we want to make error small, and h will change. I mean, here we change h and error changes. Mm-hmm. In adaptive methods, we take some error and h will change. Mm-hmm. Okay, and now maybe the most interesting part. As I said before, we should treat our equation as an infinite layer network. And here you can see how it will look. And every small block is our layer at some time t. And big block is actually just to show you how every block looks like. It change z by adding to the inputs function f at z at given time t. And to when we train ordinary networks, we need to know how we need to know gradients by with respect to all the parameters and with respect to all the inputs at every layer. And here's the analogy: we need to know same things for same gradients for every time t. And it's the connection with the theory of Pendragon, where he had this for the ordinary differential equations, these functions are called adjoint. And because theta is the sum function of time, we have adjoint for theta and adjoint for z.
But what parameters do we learn here?
We learn theta at time 0.
It's the only parameter.
Yes. Look, I want to make it clear for you. When we change theta at time 0, all our solution goes in some other way, and we change solution at time t big, and we get another loss. And this is the only thing we can change here, only the initial parameters. And okay, but these values adjoint, they show how our loss will change if we add some small variation to our parameters at time t or for our solution at time t.
Go to the previous slide. Yes, I want to make a comment about these equations, because these equations is just like continuous analog of backpropagation. In backpropagation, we need to take derivatives of loss with respect to parameters of each layer, and here you can see a theta of t equals derivative of loss with respect to theta at time t, and also we need to take derivative of loss with respect to inputs of our current layer, and we take derivative of loss with respect to z at time t.
Thank you. Okay. Now I want to show you what we will get. Actually, for these parameters, for these functions, a theta and a z, we will get new differential equations. So our forward pass will be the solving of differential equations, and our backpropagation will be the solving of other differential equations. And we need to discuss how loss depends on these parameters and z at time t big, and from as it was on previous slide, loss depends on z at time t big, and we can just take derivative by this parameter, and it will be az at time t big, and it will be enough to get unique solution for az at time 0. And loss doesn't depend on theta at time t big, because if we change theta only at this time, nothing will change. So a theta just 0, and that's also enough to get unique solution for a theta at time 0. And we can get these equations by using the definition of derivative, which is given on the last line. And here we can see the analogy with chain rule in neural networks. If we change z at some time t, we can see that loss will somehow, if we change z at time t, z at time t plus epsilon will change too. And derivative z at time t plus epsilon by z at time t, it shows how it will change. And loss will change at the time because we change z at time t plus epsilon. And the same for theta, because if you change not in our case, but in general case, if we change z, theta will change somehow at time t plus epsilon. But we know that in our case theta is a constant, and I will show it later. And the same for the second line. If we will change theta at some time t, z will change at time t plus epsilon, and theta will change in time t plus epsilon. And maybe I'll show on this picture. So if we change something here, theta and z, we can get the same equation. So you should treat it as a chain rule in ordinary neural networks, but it's true formula for in continuous time. So to get red functions, we can just write down what z at time t plus epsilon is. We can use Taylor's series to get this, and we need only the linear step, and we change time derivative here with the function f, because we know that our equation gives us this changing. And then we just find partial derivatives by z at time t. And the same for the theta, but it's actually easier because theta is a constant, and it does not depend on z. And for their theta, for the partial derivatives by theta, we get 1. And I want to say that everywhere on my slides, theta and z, it's vectors. I just formulas will be the same as for vectors, and I just don't want to overload the slides. But one is actually matrix. So now I can put these values in the first line in the definition of derivative, and we will just get these equations.
Excuse me, why is O of epsilon squared left after taking the derivative? The epsilon squared term, it's not clear for me why it's left after taking the derivative.
Why it's what?
The residual term is the same after the derivative, and
Look.
it's unclear why.
We will get O of epsilon square. It will be stay near the second derivative by time of z. And you can get second derivative by time just by take a first derivative of a function f. And I can write it if you want.
I think I understand what you're saying.
Okay. And I mean the second derivative of z will also depends on z. So when I'll take a partial derivative by z, it will remain. And but it doesn't matter. But you're right. It will remain. And okay, it's how we can get these equations. And now we can look how we can train our network. But here you should treat integral not like not like integral, but like ODE solver. So it can be early method or Runge-Kutta, and it will give you not only z at time t big, but also at every time of our grid. It's one point to make clear this slide. So on the forward pass, we can get our solution at final time just by solve our equation. And you can see that I put this theta not like function, just like constant, our initial values. And then we need to change it to train our network, and we need to get the solution of equations from the previous slide, which was for AZ and A theta. And we also can get it, but backwards in time from t big to 0. And here we can see maybe the best advantage of this approach, because you can see that we need to know that at time tau, at every time tau in our integral, and we can get it from forward pass, but we need to save the same grid on the backward just like on the forward pass. But here we can get z at time t, at that time tau, or t, solving our equation back in time. And we don't need to save all the z at time t on the forward pass. So it can take less memory.
So that's actually quite important thing, because it's known that when we would like to train neural network, we should keep in memory all activations,
yes,
in order to run backpropagation on it. Here we're not obliged to do that, because if we know the output, we can backpropagate this in order to get z of tau, and at the same time we will backpropagate the error, the gradients of our loss function.
I think it's the main advantage of this this approach.
But is it correct that I need to solve new differential equation every single layer? Like,
But it has linear complexity. It has the same computational complexity as just performing, say, forward propagation in usual deep neural network.
linear complexity, but okay, when you go into from, let's say, layer number n to layer number n minus 1,
Right.
you have new differential
No,
equation.
no. You just add new point of your differential equation.
Ah, I get it. So it's kind of iterative.
Yes,
kind of
yes,
thing,
yes. You use your previous z of t,
Okay, okay.
and then
Cool.
So let us say that this is one of the main advantages. I would not say that this is the main advantage, because there will be some other advantages as well. And it's the matter of taste, which is the main one.
Is it linear in time for implicit integration schemes?
For implicit, no.
Only for explicit?
For explicit, for error scheme.
Yeah, but you will need very large number of time steps to get the same solution, because explicit scheme is an unstable scheme.
This is right. But this is exactly what we are doing in ResNet. If we are fine with ResNet, then it says that we should be fine with the error method as well. But here we have room for improvement. Because here we can remove error scheme with the more advanced schemes like Runge-Kutta, like implicit schemes, and we could hope that we'll get more benefits at the expense of computational cost.
And this is picture from original paper. As I mentioned, for the adaptive solvers, the number of steps are different, and NFE, it's a number of steps, it's a number of function evaluation. It's the same as number of steps in our solver. And it's surprising result, and authors don't explain it, but you can see that on the backward we need less integration steps than on forward pass. So not keeping that in memory from the forward pass is not only better because we save memory, and it's better because we don't need such a grid. We can get some small, some larger grid.
So is this some adaptive method that dynamically adapts to the number of steps?
It dynamically adapts to keep your error in some unchangeable values.
you just fix an accuracy, and method say you how many steps you should do.
And what would be the grid?
Yes.
One question from me. Consider the derivative of our loss with respect to theta t. Why there's theta 0 inside the integral? Why not theta tau? I understand that if theta is constant, then it doesn't matter.
Yeah.
But if here we consider the general case,
You can just add equation for theta and go backwards in time, and you will get the same constant each time. Because the equation for theta is that in time theta time t is just theta time t big.
I think the question was how this equation change if we say that theta is some function of t.
Well, it's big formula. We can't. It will depends on some this function which you take, and if theta will given for us as a differential equation, it will be depends on function f theta. If we treat this f as f z, and we need to get some f theta to see the evolution of theta, and it will depend on this function.
okay, so the equation is right, is correct only in assumption that theta doesn't change in time, right?
Yes.
And to get the derivative of our loss with respect to theta 0, we need to integrate from t large to 0.
Yes.
Mhm.
Okay, and now I'll show you experiments of offers. As you can see, they chose NIST as a data set, and actually some of these results are doubtable because ResNet 6 is it was some downsampling layers, then 6 ResNet layers, and then fully connected layers. And they say that some of advantage of this approach because that they can use less parameters to get the same test error. But the last line, it was my experiment. I just take one ResNet block instead of 6 to get the same amount of parameters as in ODE net, and I get the same test error. So I can say that that this approach gives us this advantage of getting the same error on less amount of parameters.
But in your ResNet with just one ResNet block, have you used the index of the layer as additional input?
No.
No.
It was just
So
a regular and number of parameters is the same because parameters in ODE net is the same as the parameters in ResNet because it's they have the same function f.
Okay.
But
so in some sense, I may say that ResNet 1 is simply recurrent neural network with a predefined number of steps.
Yes.
Mm-hmm.
So it was the second advantage, and I can say that actually it is an advantage looking on these experiments. We need more experiments if we want to say.
Can you say, your f function is a neural network itself, and it has some number of layers, yes?
Yes.
Can we say that the memory consumption is not O of 1, but O of L star, say, where L star is the number of layers in your f? Yes, but then it is not O over 1.
No, it's
Maybe this by this they mean only those this part of memory which need to save solution, not to save our network, but save our solution on forward pass.
It's additional memory to backpropagate, to forward and backpropagate.
So it's assumed that the number of memory needed to train this small neural network with weights theta. So this small neural network is much smaller than the initial ResNet.
Yes.
And this is why the amount of memory needed to train it is negligible in comparison with the amount of memory needed to train the whole conventional ResNet.
It's not all memory, and actually you're right, we need to write O of L plus O of L for training and O of L for saving just some network. But and this is column only for training. And what I can say is that ODENet takes much more time for training because number of layers, number of this implicit number of layers, which is number of function evaluation, which is number of steps which our solver takes, it's can be big and it more time consuming.
And how do you choose this number?
The best approach is not to choose this number, just to take this adaptive algorithm and just to...
But you need to fix T big.
Yes, and I need to fix the accuracy what I want to obtain, and they just fix accuracy.
So you've taken t big equal to 1?
Yes,
Okay.
but I think it doesn't matter, because if we change t big, we just get another steps, which will be in t big times bigger.
Yes, but with bigger number of layers, you do a bigger, more changes to the trajectory. So the actual Z, the final Z would change.
Yes, yes, this is right, but we need to fix t big. And in all this experience it was 1.
Mm-hmm.
Can you say that L hat is bigger or smaller? Bigger?
Bigger, bigger.
How
Much bigger. In this experience, in six times, I would say. If L big is a 6, for example, L hat is a 26 or 30.
For explicit or implicit scheme?
Implicit. And finally, just some experiments which I made. Here I just put 160 epochs, and I didn't train well, so it's preliminary results. I just want to show you some numbers. Here you can see better difference in ResNet 6 and ODNet and ResNet 1. And you can see that actually ResNet 1 gives us the same quality, the same accuracy as ODNet, taking the same number of parameters. So that overstate that its advantage, I can say with this experiment it is not advantage. So we need more parameters to get better accuracy, and actually almost the same as ResNet. But it's just time in seconds. You can see the times. And in the last row, I tried to remove explicit dependence on time in F, just removing that additional channel from, as I said, they added depending on time by adding an additional channel to every layer, and I remove this to look what I will get. And
there was a dramatic drop at 1.5%.
yes,
Interesting.
but it's not that dramatic as I expected. Okay, that's all I wanted to say.
What about normalizing flows? Will it be in the second part?
Yes, normalizing flows is connected with fjords, and Sasha will tell it about the next time.
Okay, any more questions? If not, then I will conclude with some remarks. From my point of view, well, the reason why I do like this paper and why I do like this direction is because it allows to have a different look at the same model. So we know that residual networks work. We had some intuition why it works. We know that it prevents from vanishing of gradients, blah, blah, blah. Here's a completely different tool. And from the different viewpoint, we can interpret this net as just an Euler scheme of a neural differential equation. We know what was the initial differential equation, and we know that we could actually use different ways for solving it, not just Euler scheme. From my experience, this is always very fruitful to have a different viewpoint at the same model. Just like it was done with the dropout, which was viewed from Bayesian viewpoint, or just like it was done with boosting before. So that's always good, and that's why I like such papers, which suggest us new viewpoints for the same for the old models. So that's it. Let us thank the speaker for interesting talk. And come back in a week when we'll have part 2.